Hello everyone, welcome to this lecture of hyperbolic geometry. In this lecture, we'll prove that isometry of the upper half plane with respect to hyperbolic metric is isomorphic to the group generated by PSL2R and reflection with respect to y-axis. So let us begin. In order to find the isometric group of this upper half plane, so we'll be first give an explicit formula of the hyperbolic distance between 2 points of the upper half plane. So let us take 2 points. Let ZW be 2 points in the upper half plane. So again, this upper half plane is equipped with the hyperbolic metric dx squared plus dy squared by y squared. So we'll prove the following thing. So the hyperbolic distance between Z and W, so this is equal to log of mod Z minus W bar plus mod of Z minus W divided by Z minus W bar minus mod of Z minus W. Okay, so now suppose we take this point to be Z equals to IA and W to be equals to IP. So we have showed that, so the geodesic joining this IA and IB is the imaginary axis. So this is this, imaginary axis. And so if I take any other differentiable path, gamma, and if I call this alpha to be the vertical geodesic joining IA and IB, so we have proved that length of gamma is strictly greater than length of alpha. And length of alpha, so this is nothing but log of B by A, and alpha is the geodesic, meaning length of alpha is exactly equals to distance between IA and IB. So therefore these 2 points Z and W, where this Z is equal to IA and W is equal to IB, so already proved this thing. So distance between IA and IB is log of B by A. So if I put this Z equals to IA and W equals to IB in this formula, so we'll get the right hand side of the star equation to be log B by A. So therefore, so this equation, it holds for Z equals to IA and W equals to IB. So now let us take any other 2 points ZW in this upper half plane, so that may not lie in the imaginary axis. So this is my imaginary axis, and I have proved this thing that if I take IA and IB, so distance between IA and IB is equal to log B by A, which is nothing but the right hand side of the equation star. Okay, so now let us take ZW, some points in upper half plane which does not lie in the imaginary axis. So then we know that suppose it does not lie in a vertical line, so there exists a semicircle passing through this ZW orthogonal to the real axis, and the center of this semicircle, it lies on the real axis or x-axis. Suppose this semicircle intersect the real axis in x and y. So now if I take this transformation, so T of U to be equal to your 1 by x minus y, U minus x divided by U minus y. So which is nothing but, so U by x minus y minus x by x minus y whole divided by u by x minus y minus y by x minus y. So corresponding to this transformation, so this is a Mobius transformation. So T is a Mobius transformation. So T also belongs to your SL to R. So if I take this matrix, so this belongs to your SL to R. And this SL to R, it acts on this upper half plane by isometries. Okay. So therefore, so this T is an isometry of this upper half plane. And also note that, so if I take so T of, so if I take T of the semicircle, so T sets the semicircle to your the imaginary axis. If I call this semicircle to be C, so this isometry tree, it takes C to your this imaginary axis. So why this is true? So because so T of this x, so this is 0, and T of y, it is infinity. So T is a Mobius transformation. So it will take the circle to either a straight line or a circle. So here, so this semicircle, so this x is going to 0 and y is going to infinity, and T of C, it has to be the straight line, and the straight line will be the imaginary axis. So this T, it sends this semicircle to this imaginary axis. So therefore we can assume that, so we can assume, so T of Z to be equal to your IA and T of W to be equal to your IB, and this A is less than your B. So next is, so this already we have proved that, so Mobius transformation preserves cross ratio. So what is the definition of cross ratio? So Z1, Z2, Z3, Z4. So this is defined to be Z1 minus Z3 by Z2 minus Z4 divided by Z1 minus Z4 times Z2 minus Z3. So if all this Z1, Z2, Z3, Z4 lie in the complex plane, so then this is my definition of cross ratio. So this Mobius transformation, it preserves cross ratio. So therefore, so T of Z1, T of Z2, TZ3, TZ4. So if I take this cross ratio, so this will be equal to your Z1, Z2, Z3, Z4. So we have this points ZW. So now let us think of the complex plane. So this is my complex plane. So the upper part is your, so this one is your H2. And the lower thing is your, you can say H2 bar. So Z and W, so these are my points in the upper half plane. So if I take the conjugate Z bar, so it will be in the lower half plane. Now, if I take this 4 points, Z, Z, Z bar, W, W bar, and if I take this cross ratio, so T is a Mobius transformation. So this T can extend to C union infinity. So T will preserve the cross ratio. So T Z, T Z bar. So this cross ratio will be preserved. So this will imply that, so ZW, Z bar, W bar, so all these are in the complex plane. So from this equation, if I take the mod, so what we'll get? So mod of Z minus W times mod of Z bar minus W bar. So this divided by mod of W minus Z bar times Z minus W bar is equal to your mod of A minus B times mod of A minus B divided by mod of B plus A times. So here, note that T of Z is equal to your IA, T of W is equal to IB. Yeah, so after taking mod, so mod of I is 1, so therefore we have this right hand side, this one. So this will imply that mod of Z minus W divided by mod of W minus Z bar is equal to your B minus A by B plus A. We can remove the mod here because B is greater than A. So this will imply that mod of Z minus W bar by mod of Z minus W is equal to your B plus A by B minus A. And therefore, now if I apply this componendo and dividendo and take the log both side, so what we'll get? Log of mod of Z minus W bar plus mod of Z minus W divided by mod of Z minus W bar minus mod of Z minus W is equal to your log B by A. And so log B by A, so this is nothing but equal to distance between IA and IB. So this already we have observed. And as T is an isometry, so distance between ZW is equal to distance between T of Z and T of W, which is nothing but equal to distance between IA and IB. So therefore, from these two equations, so what we have? So distance between ZW is equal to your log of mod of Z minus W bar plus mod of Z minus W divided by mod of Z minus W bar minus mod of Z minus W. So now let us come back to the isometries of this upper half plane. Okay, so let me first define this group. So let S star L to R, so this to be your the set of all matrices such that determinant of this matrix is plus minus 1. So that is AD minus BC is your plus minus 1, and P S star to R. So this is the quotient of this S star L to R. So this is just plus minus identity. Okay, so now what is the theorem? So the group, the isometric group of this upper half plane is generated by Mobius transformations in PSL to R together with the map z equals to minus z bar and is isomorphic to, and this group isometry of this upper half plane is isomorphic to P star L2R. So therefore, so this isometry, so what we have to prove that isometric group of this upper half plane is generated by the elements of this PSL to R and the map z equals to minus z bar. So also note that, so the group PSL to R is a subgroup of isometry group of this upper half plane of index 2. PSL to R, it is an index 2 subgroup of this isometric group of this upper half plane. Okay, let us try to prove this theorem. So let us let phi to be an isometry of this upper half plane and let I to be the imaginary axis. So as phi is an isometry, so phi of I will be a geodesic. So phi of I, again, it will be a geodesic. So it will be a bi-infinite geodesic because I is a bi-infinite geodesic. So now again, so there exists A belongs to your SL to R such that, so A of this phi of I is equal to I. So this already we have seen. So suppose so this is my imaginary axis. Let us take this to be my imaginary axis. And what this phi is doing, so phi is taking this imaginary axis to some other geodesic. Let us take this to be my phi of I. So we know that there exists an element of this SL to R such that A of phi I is equal to your I. So A, you will take this geodesic phi I to your I. Okay. And this PSL to R, so this is quotient of this SL to R. So therefore, without loss of generality, we can assume this A to be in PSL to R. So without loss of generality, we can assume A belongs to your PSL to R. Okay. So therefore, so what we got, so we get an element of this PSL to R, which takes this phi I to your I. Okay. So therefore, because A takes this phi I to I, so if I take this A compose phi, so it will fix this imaginary axis I. So A of phi I is equal to I. So this implies A compose phi fixes the imaginary axis I. So again, also note that, so this also we have seen that PSL to R, it is a subgroup of this isometry of this upper half plane. So this we have seen in some previous class. So therefore, A compose phi, it is again an isometry of this upper half plane. So we have taken phi to be an isometry. A is an isometry. So A compose phi, again it is an isometry of this upper half plane. Okay. Okay, so now this A compose phi, it fixes this imaginary axis. So therefore, so there exist. So because this A compose phi, it fixes this imaginary axis. So it will take I to some lambda I, right? So A compose phi of I, so this will be equal to some lambda I for some lambda not equal to 0. Okay, so now let us take, so let Pz to be equal to your 1 by lambda z. So again, so this scaling, so this is again an isometry of this upper half plane. So this again, it is an isometry of this upper half plane. And now if I take this B compose A compose phi, so this will fix this imaginary number I, and B also fixes this imaginary axis, because B fixes I, imaginary axis I. So this proves that, so B compose A compose phi, it fixes 0 infinity and the point I. So now suppose B compose A compose phi, it fixes 0 infinity. So what it can do, it can take 0 to infinity and infinity to 0. It can do this thing. So if this is the case, so then what you do, so then let us take Cz to be equal to your minus 1 by z. So again note that, so corresponding to this C, so we have this matrix. So C corresponds to this matrix 0, minus 1, 1, 0. So determinant of this matrix is again 1. So this C will correspond to an element of this PSL to R. So C is again an isometry also. So C, it is an element of this PSL to R. So again, it is a subgroup of this isometry of this upper plane. And now what we have, so this, let us take this isometry C compose, B compose, A compose phi. So this isometry, it will fix this 0. So this isometry again, so this will fix the point infinity. And also because C fixes, so C of I is equal to your I. So C compose, B compose, A compose phi. So this will also fix this I. So already you have seen that B compose, A compose phi, it fixes the imaginary number I. C fixes the imaginary number I. So therefore C compose, B compose, A compose phi, it fixes the imaginary number I. And again, so this C compose, B compose, A compose phi. So this is an isometry of this upper half plane. So this fixes the imaginary number I. It fixes 0 and infinity. So one can check that. So check that C compose, B compose, A compose phi, it fixes the imaginary axis I pointwise. Okay, so we have started with an isometry phi, and we are precomposing with the element of this PSL to R, such that that composition, it will fix the imaginary axis I. Okay, so now let us take, Z, in the upper half plane. And let us assume, and let C compose, B compose, A compose phi of Z is equal to your U plus IB. So also this isometry C compose, B compose, A compose phi, it fixes the imaginary axis pointwise. So what we have, so C compose, B compose, A compose phi of IT is equal to IT for all t greater than 0. So we have this picture here. So this is my imaginary axis I. So C compose, B compose, A compose phi, it fixes I pointwise. Now if I take some point Z here, the image of this Z, so this, what will prove that, so this will either equal to Z or it is the reflection with respect to the imaginary axis. Okay. So this is Z is equal to X plus IY. And suppose this is my U plus IB. So what will be proving that? So this U is equal to your plus minus X and B is equal to your Y. So now let us take this distance between X plus IY and IT. So I'm taking any point here, IT. So I'm taking the distance between Z and IT. And now we'll apply the isometry C compose, B compose, A compose phi on these 2 points. So the distance will be preserved. So this will be equal to your, the right hand side will be equal to your distance between U plus IB, and the point IT is fixed by the isometry. So we have IT here. Now you have the distance formula, explicit formula of that distance. So what we have, so this will be equal to mod of X plus IY plus IT plus mod of X plus IY minus IT divided by mod of X plus IY plus IT minus mod of X plus IY minus IT. So we have taken log of this. So log of this thing will be equal to the distance between X plus IY and IT. So this will be equal to log of mod of U plus IB plus IT plus mod of U plus IB plus IT divided by mod of U plus IB plus IT minus mod of U plus IB minus IT. So we have this thing here. Now you can remove the log from the both sides and you can do some computation and eventually we'll get this equation. So x by t whole square plus y by t plus 1 whole square times p is equal to u by t square plus b by t plus 1 whole square times y. And this is true for all t greater than 0. So now if I take t tends to infinity, so what we'll get? So this will imply that, so if I take t tends to infinity in this equation, so what we'll get? B equals to y. And again, if I put b equals to y in this equation, in equation 1, so if I put this thing, so what you'll get, thus x square is equal to your u square. So this implies that u is equal to your plus minus x. Okay, so therefore, so what we have proved that, so either u plus ib is equal to your x plus iy, so that is equal to your z, or u plus ib, so this is equal to your minus x plus Iy. So this is equal to minus z bar. So therefore, so what we have proved that, so this C compose B compose A compose phi of z is equal to z, or C compose B compose A compose phi of z is equal to your minus z bar. Okay, so this implies that, so this composition of this isometry, so this is either equal to identity map, or this is equal to C compose B compose A compose phi is equal to your this reflection with respect to the imaginary axis. Okay, so therefore, so this will imply that, so now what we'll do here, so this phi is equal to your A inverse compose B inverse compose C inverse, or this phi is equal to A inverse compose B inverse compose C inverse compose R. Okay, so this ABC, it belongs to your PSL to R. So this will imply that the inverse also, it belongs to your PSL to R. And R is just the reflection with respect to imaginary axis. So therefore, we have proved that phi belongs to the group generated by PSL to R, and the map z equals to minus z bar. Yeah. So therefore, what we have proved that this isometry of this isometric group of this upper half plane, it is a subgroup of this PSL to R and this map generated by this. Okay, so also observe that, so this map reflection is an isometry of the upper half plane. And also we have seen that PSL to R, it is a subgroup of this isometry of this upper half plane. So therefore what we have, so this the isometric group of this upper half plane is the group generated by PSL to R and this reflection map. Yeah. So if you know about orientation preserving or orientation reversing, so this PSL to R, so this is orientation preserving isometry group of this upper half plane. And the map z goes to minus z bar. So this is orientation reversing isometry. Okay, so I'll stop here today. Thank you.